Okay.
Yeah.
Hopefully more people will filter in. We normally have a few more, but I think maybe with the holiday, it should be us. But yeah, I'm excited to hear about this talk. So, Dwight, thank you so much for being with us. Dwight is a assistant professor at Morgan State University now. He got his PhD at UT Arlington, if I'm correct about that, and then did postdoc at Iowa State and a postdoc position at Pomona before joining the faculty at Morgan State University. And he's going to talk to us today about extremal equations and algebraic methods. So thank you so much for being here, Dwight, and take it away.
Thank you very much. As seen in the first slide here, the title slide, I am at Morgan State, and I guess I'm taking OU, the Zoom meetings here, but there's organizers all around, and thank you so much for doing this, Christian Wine, and everybody for joining. So I like to start out a little bit of some of the journalistic questions: who, why, what, or dipping the wind, I guess. And I come to this talk recognizing that I'm a bit tired, and this is not meant to be super precise. I do want to share mathematics and share a little bit of who I am, and give an idea. Like this is something I've been working on with groups of people you'll see soon, and it's really exciting to me. So I'm actually going to say that I'm a bit excited. So a bit tired, a lot's going on in the world, locally, globally. People are facing so many things right now. And I think it's also important as I talk to people facing different things, whether in different countries right now, that a lot of us do get enjoyment from doing mathematics. And I'm excited to be able to share some of that. And also, I'm a Black man in super algebra research, and I think about this a lot because I'm also blessed to work with another Black man in super algebra research. And this work I'm going to be sharing has many tentacles. I'll start actually to the right, Jonas's presence, and this work, I think a lot of it is born from what we've been doing. What we started at Iowa State, Jonas is at Iowa State, and I was a postdoc there, worked with Michael Young, worked with Jonas, separate projects. And right to left, Demeter is my PhD advisor at UT Arlington, and trying to get him involved in some other ideas, because there's kind of a big picture that I will hopefully be able to draw somewhat. Ermac, a PhD student currently at Carnegie Mellon in computer science, like machine learning. She is going the smarter way, some would say, but she has a lot of skills and was able to work on this idea of reduction algebra, the stream equations as an undergraduate from Monash College. And my doctoral sibling is Saber. He's also been looking at reduction algebras most recently. And so I'll touch a little bit of what we've looked at. But the main idea here is I want to solve problems and symmetry solve problems. That's how I think about algebra. You could say that is my origin story as a super algebraist. Or more precisely, someone asked me did I want to work classical problems or super problems, and that was a no-brainer. So when we see the title, you can think of extreme equations as the problems we want to solve. I put extremal in parentheses because some of this work or a lot of this work is born from Zelibenko, and he has a particular definition about extremal that deals with the algebras themselves. But we can just think of all these different kind of equations that run the gamut in physics or in other areas of life and modeling. And we're looking for solutions, and one way to do that is through algebraic methods. I'm pretty much going to talk about one method, so maybe I should have kept it singular. But we've seen hopefully ideas of representation theory and all that. I can get into detail, but again, I'm looking to solve uh, equations using algebraic methods. And what is algebras? I find that we don't talk about them enough, but we have a vector space with a product, and all the operations work well together. So you can think about the scalar multiplication on the vector product, excuse me, on the vector space. Well, you also have a product, and we're going to say that they're compatible in different ways. I'm not writing all that out at the moment. Because again, the algebras that you can care about, or I care about in the beginning, I guess, are algebras of linear transformations. So some fixed vector space, we can think of the ground field as being the complex numbers, and L of V, your script, Also can be written here as n to v, the endomorphisms from V to itself. We also have algebra matrices. In a lot of cases, V is finite dimensional, and as we see, you can consider the transformations of matrices, some choice of bases, and all that. So these are both algebras. The algebra linear transformations, the algebra matrices, they're vector spaces over C, but they also have composition of functions, multiplication of matrices. These are the heart, I feel, in some ways, of what we're getting into. And so we want to take our favorite algebras or abstract algebras and realize them as algebra linear transformations. Transformations move things around. And the idea is, can we move from a solution to a solution of a particular equation? That's like the motivation or what I find very interesting about this idea. Someone studied all this abstract stuff and but it's born from maybe very concrete questions or even this big idea like, can I find more solutions if I have one? How do I move around in a solution space? Can I stay in a solution space? So that's the general goal of uh, what I do. And I guess you can say, well, where can we start? We'll start with a particular equation. We'll start with a particular algebra. So Laplace's equation and SL2. I'm certain there's people in this room who have a lot to say about Laplace. In fact, I think that I've been to the first talk here and Laplacian came up, and of course solving PDEs and all these different things that have been shown. Laplacian shows up in a lot of places. I'm not here to convince you of the importance of the Laplacian at the moment, but we can take it as a linear transformation, in this case, from complex polynomials back to the complex polynomials. Given a polynomial, we'll look at the sum of the second degree partials, or the second partials, and we'll get back another polynomial. And this is the linear operator. Everything's really nice. So it's our first kind of test here. So here's our equation. Delta of f equals 0, Laplacian f equals 0. I was thinking about this the other day, like this is Laplace's equation. I need to do better in life. I need to have my equations. It's kind of weird. Like, how do you have an equation named after yourself? I don't know. But I will also say keep citing people. Cite me too, right? So kind of hypocritical. This equation can also it's the defining equation of the kernel of this map. So you're already kind of seeing we can just ask like when is Laplacian gonna give us out the output of 0? Same thing as asking the kernel of delta here as a linear transformation. So we can kind of just use different words and maybe that give different perspectives and hopefully they come around and connect. They're not too far apart. Now here's the algebra, and I'm using algebra more generally. Like I said, a vector space with some kind of binary product, some kind of multiplication, um, not necessarily associative. And in fact, the algebra in front of us, or the start of it, is certainly not associative. We take three-dimensional vector space, where the basis can be F, H, E, so the span of F, direct on the span of H, direct on the span of E. And we're going to define a product on the basis elements, but we should be careful. It's not really a product on the basis elements because you see things like 2F is not in the basis, but it's part of the vector space that we span. And so we're going to extend this by linearity, so our product's actually bilinear. But this multiplication table, written maybe not the same way most have seen it, will give us the idea of how the product works, this Lie bracket over the entire vector space. So one thing to show, we have anti-symmetry. If you look across the diagonal, 2F minus 2F, when you first order with the first column representing the left entry, the top row, the right entry, and so on, or not really so on. We also have that the bracket of the element with itself is 0. So these are all key parts of a general definition of the algebra. The last part kind of missing is the satisfying the Jacobi identity, which is a good replacement of the or not having associativity. So the pair, this vector space with the bracket will be called the special linear algebra degree 2. And degree 2, well, we can realize this is the first time we're realizing our algebra as some kind of, our abstract algebra as algebra matrices. So this is the way I like to think about it. So 2 at times, where we have these 2 by 2 matrices. H is some diagonal matrix. F, lower triangular matrix, and E, are upper triangular matrix. 1 second, please. I don't know if I can make it quite fast. Thank you for the pause. So now that we have an algebra and an equation, I want you to take a little stroll through the theory of primitive vectors. Again, not going to be highly concerned with all the details. We already saw this triangular decomposition, like a 3-part. And I mentioned earlier, it's not just that we have 3 subspaces joining as one to be the full space. It's very particular that this middle space is we call it a Abelian algebra. It's actually a Cartan subalgebra G. But we saw, like, if you take H with itself, you get 0. So okay, that's not really saying much about this idea of being commute. The big thing, if you just look back at the matrices, we had this upper triangular matrix, lower triangular matrix, and what those were nilpotent matrices. So if you take powers of them in a sense, they go to 0. You don't have to do too much with E or F to get to 0. And so we have this decomposition of our Lie algebra, and we said that the algebra already was realized as algebra matrices, which means it's linear transformations in on space. So if you have M, and M is a vector space that G is acting on as linear transformations, then we can think about, well, E is going to be a linear transformation. We can ask what's its kernel in this sense. So this M plus is going to be the kernel of E when we think of E as a linear transformation on M. And we'll call this the space of primitive vectors. And it's a space that lives in M plus, so it's a subspace of M. And one reason M plus, or these space of primitive vectors, are important is because in a certain instance, we can decompose our vector space that we're acting on, moving things around, into these subspaces where on the right, we're taking primitive vectors, M, and then we're letting G map M, all the elements of G act on M. So in other words, well, E, we just said M is in the kernel of E, so E would take M to 0. H is diagonalizable or is a diagonal matrix, so it will act like a scalar, so kind of stay in the space. And then F will kind of move us around. And so this idea is very algebraic in a sense, but it's important to me. It's like, okay, primitive vectors show up and they have a role. So a lot of my research, even from graduate school, was not necessarily determining primitive vectors, but then what kind of algebras do we get, and then decomposing them. So decomposing modules is a classical kind of question of representation theory, as much as trying to decompose natural numbers into primes. Like, I mean, what are the building blocks of our vector spaces when they're thought of as a place where our algebras act and move things? Well, this is kind of the hearts, and I hope I'm not moving too quickly because, well, some of these things may have been seen by you all, but I have kind of like a back end to this, and it's going to have more notation. So please, if you want more details and want to be more precise, we can talk a little bit about that as well. Here's one of the big jumps, reduction algebra. So the idea is that we want to connect Laplace's equation in primitive vectors. So we have, again, one idea, just I'm solving an equation. This other idea, I have a module, I have a representation, this space, vector space, that this abstract algebra, can linear transformations on, and we can decompose it in particular case. So this is like the exclamation. Like, I didn't simulate or whatever, I'm just telling you. Reduction algebras act on the space of primitive vectors. Like, if you want to remember anything about this talk in terms of reduction algebras, they act on the space of primitive vectors. And that is, I mean, like we saw, there's a case where we can think of primitive vectors in some ways as another type of building block that decompose a module. They span themselves like these submodules that build up the big vector space. A module here, again, any vector space that algebra is acting. And this is where the connection is. We saw the Laplacian as a linear transformation from the polynomials and polynomials. We're going to realize the Laplace equation or solutions to it as primitive vectors. So your first question you might ask, what's a reduction algebra? Because that first sentence, I'm like, does all these great things. Well, I'm not going to break the flow of the current part of the talk. I'm just going to say it's a quotient algebra, or you can see there's this double coset space that has what's so-called diamond product. I'll bring this up in a different case towards the end of the talk. But it's a particular type of algebra. The point is this key connection, key ingredient. It's a classical thing. Goodman, Wallach, many others have used this or written about it, that if we wanted to, figure out which algebra or what realization of this of SL2 algebra is going to help us solve the Laplace equation, we have this nice triple, an SL2 triple, meaning it's just like FHE before with the matrices, the multiplication table is going to hold. So it's just some realization of SO2, but now in terms of differential operators, getting into the idea of building up our equation to be solved. So we have affine transformations of familiar characters. On the far right, we have the scalar multiple Laplacian. In the middle, we have Euler operator, or again, some kind of transformation of it, affine transformation. And on the left, some people say it's like a radial component or radio operator where kind of think of a length operator, like norm squared here. But okay. So the construction, I will say, relies on using the infile algebra, which is, you can think of that as the algebra of differential operators with polynomial coefficients. Some people are more physics, I guess, thinking from the idea of physics, when you think of annihilation and creation operators, and you can go that route as well. In fact, that's kind of the basis for my claim to be a mathematical physicist in some days, depending on time. But this is what I will say. Going back to what I mentioned about Ermac. Ermac, she did a lot of good work on trying to make concrete the writings of Delebenko. So Delebenko talks about these extremal equations and runs this example through one of his papers to try to talk about how you can solve equations using reduction algebras. But there's missing some proofs at times, and it was just really good to see someone be able to get these generators of the algebra concretely. So on the left, on the beginning of this set, you see this kind of capital D tilde I. We can think of that as the partials. I actually have these this is very much not respectively. So the DI is more like the partial I. And like taking derivatives in a sense, this capital H is like this little h where we set it acts like a scalar. So it moves things around, just augmenting them. And we have this kind of multiplicative factor, the xi. So this comes about by taking the Val algebra and quoting out by left ideal that you can generate using Laplacian. But there's a little bit more about how we localize this, and there's actually more because we're looking at we want not just a um, we want to actually make these quotients, so we don't take the Val algebra anymore. We look at this normalizer of the ideal inside the Val algebra, and there's more details. Again, I'll give a super case later and kind of walk through some of the ingredients in a little bit more detail. The main point is we are able to get some kind of algebra, and this algebra is going to act on the primitive vectors. Uh, Primitive vectors of what module? Well, SO2, as we saw before, being differential operators, acts on polynomials, and the payoff is something like this. So we take these elements, and if we consider just the second set of them, these xi plus this rational function and these xi squared di. Let's call it t, just because write it over and over again. And I think this is pretty cool because okay, t of one is supposed to be xi. I'm not saying exactly how all these things work, but if you apply t again to xi, you get this interesting sum. But I think the most interesting one to me is like keep going. And so if you take t, like okay, t of one, then t of that image, and go on and on, we get this another sum. And you say you can trust me, or I trust her, man. And we calculated this. This is in fact a harmonic polynomial, meaning it is a solution to the Laplace equation. And the idea is that we can keep going and going and going, and you can also use the other operator, this di tilde operator. So for instance, if you were to act, I think I have a nice already, I'll just say that. So if we say, okay, what if we go t apply twice to one, or t apply to one, then the image, and then we want to now apply this di tilde. Well, it takes us kind of back to a lower degree, from the second degree polynomial down to something else where another sum. And then we can kind of just keep going back and forth. There's some theory, as I jump back to the slides, there's some theory that says that because the polynomials are, it's a simple module of the Val algebra, there aren't any submodules, um, well, outside of itself and zero. This space of solutions is now a simple space or a simple module of um, this SO2 realization that's been turned into this higher algebra. More plainly said, the Zellerbank, excuse me, this reduction algebra that we have built with these generators, di tilde and xi tilde plus the sum, acts irreducibly on the space of harmonic polynomials. So the idea is we start with just one, the number one itself, the polynomial one. We can generate all solutions from the Laplace equation, at least the polynomial solution. So that might not be enough for some people, but this idea of being able to figure out an algebra that can work on solutions and stay in the solution space, linear transformation in the solution space is pretty nice because you can kind of expand it to other ideas. So this is like the first payoff and motivation for looking at other type of reduction. Any questions so far? Because we kind of moved through some things.
So one thing that just notationally I'm a little bit confused about is what the h tilde is. So it seems like xi is like multiplication by x, which takes a polynomial to a polynomial, or by xi. Di is derivative in the ith coordinate. What's the h?
Yeah, very good question. So the h, the first time we saw h was in the Lie algebra SL2, and then we realized that element as some kind of like Euler operator looking element. So it's like a sum of the x and the itself. And then as we continue this process, we're going to embed in larger algebras and quotients. So it takes on that feel of kind of the Euler operator still. Right? So it acts like a kind of like the scalar in this.
Thank you.
So I said, thank you, question. That's end. Okay, this is not the end. I said I promised I was gonna show more. So this is kind of like the first part. Okay, this motivation. So this is where I'm gonna go more into just like showing kind of the heavy machinery. You can say it's extra stuff, it's super stuff. This is the first paper I wrote with Jonas. This idea. We want to start off with a least super algebra. It's 5 dimensional. It's called OSP 12. I'll give a basis for it. But this big fat G um, is going to be kind of two copies of one OSP 2. So you just have like ordered pairs of some 5 dimensional vectors. Let's say that. The super part is that there is the idea of parity, and so we have um, we have three even elements in the basis, two odd elements. This is not this is something that is concerning when you're computing, but in the current moment, I think it was best to just kind of state it. The point is that when you have one copy OSP 12, you can put it into two copies, like diagonally. So every element of OSP 12, say you have X, it's going to go to X times. And this theory so far, I said there's a lot of details, so you want to work with kind of like very nicely algebras or nice enough for us. And that is when you take the bracket of G on this bigger algebra, yeah, that produces a module. Like it's acting as linear transformations of big G. And then that module itself would decompose. So when we say a reductive image and things, we're basically saying that the adjoint representation or this idea of looking at G as a vector space itself, that little g moves around linear transformation, and that big module decomposes. So in other words, big G decomposes as little g modules. Kind of like and this is and kind of important to the theory because one, when we decompose in this idea of a reductive image, we also have reductive complements. So in other words, big G is a little g module, but it's the direct sum of two little g modules. So at least we can express as such. So we have factor P, factor little g. So my claim again that this part is just more machinery, more into a different case, but just kind of showing the notation and what the ingredients behind building up a particular reduction algebra. I mentioned this Cartan subalgebra of our OSP 12. It's a one-dimensional space, and that's going to be the span of this capital H here. So more precisely, OSP 12 is a least superalgebra. Our little factor G is a copy of OSP 12 seen inside big factor G. And so what would be the Cartan subalgebra OSP 12? We're now going to look at like a copy of it in big factor G and represent it by the span of capital H. Now, we need this multiplicative set. I mentioned word localization earlier. This is going to be what we're going to localize with. It has to do with kind of weight theory. But basically, we think of this capital H, and we're adding or subtracting natural numbers, integers, and we want the monoid that generates. So we just want to be able to stay in the set that we're creating. So let's go back to this OSP 12. If you've never seen it before, I said it's going to be 5-dimensional. I'm going to represent the elements with these 5 here. So we have x minus 2 alpha, x minus alpha, h, x alpha, x2 alpha. The alphas come from this idea of these roots and weights and all these things. It's a way to get the structure of the Lie superalgebras or the algebras as well. So what's nice is that if you look at the middle elements and the outside 2, that is a copy of SL2, 3 dimensions, like our FEHB4. The new thing with superalgebras is that we have these things like kind of odd elements. So we have x minus alpha and x alpha. And there is still this product on this vector space. It's it's instead of called a Lie bracket, it's called a Lie super bracket, and now it has to respect the parity that you put on the elements. So if you take, for instance, x minus alpha and x alpha, you get basically h. Well, x minus alpha was odd, x alpha is odd. Their product is going to be an even element, it's h. So that's what we mean by respecting parity. And you can see all the brackets here. I wanted to give a preview before showing them, but these are the different types of brackets you get with the so-called super commutator or this Lie super bracket. So another presentation of multiplication table. And then we have the same idea as triangular decomposition, but now we kind of see it in the more generic notation. The n minus is this kind of lower nilpotent parts of the Lie superalgebra. The factor H is the Cartan algebra, this middle part, if you will, and the n plus is the upper nilpotent part. And the upper nilpotent part is very important to this theory because if we had E, and we said the kernel of E gave us primitive vectors. Well, one thing you could imagine is that was a single linear transformation. But what if you had, say, n plus, whose dimension was greater than 1? And then you now ask what vectors are in the kernel of each kind of linear transformation of n plus, or each element of n plus. So now we get a system of equations. And that system, the solutions to that system equation would be our primitive vectors. There's another definition of primitive vector. This is kind of actually implying that they're primitive vectors, but that's good enough for starting with Lie algebra or Lie superalgebra and working to some set of equations that Zelivenko would call stream equation. So here, this is OSP 2. We're going to be working with that factor G, big factor G. So we have like the diagonal versions of of everything you see below. Okay, this is where I find the fun in some ways, the more fun. Well, if we take our factor H, we can look, it's a non-associative algebra, or generally, I would say Lie algebra is a non-associative. So what happens here is we can look at an embedding in associative algebra called the universal enveloping algebra of factor H. This is actually commutative because all the elements H commuted with the regular Lie bracket or the Lie super bracket. So we get a commutative algebra, which is U of bracket H. In theory for localization, we have commutative rings and multiplicative sets. You can do a lot of things. You do a non-commutative ring, but not just. So this thing here, R, we're gonna go from looking at the complex numbers of the ground field to extending our scalars to R, because complex numbers are included in this universal enveloping algebra and then therefore included in this localization. So what this means, another way to put it is R is here. We get functions, rational functions, in this capital H. So you just think of like 1 over H minus 1 and so on and so on. Those are going to be our scalars. And then we have all these elements in the diagonals. Okay, so before we had like x alpha, x minus 2 alpha and everything. So just think of beta as a placeholder. Well, then we're going to have capital X beta, and that's in the diagonal. So this is our copy of OSP 1, just writing the elements. Another way, I mean, we're going to be a little precise. We're in this tensor product, and we can identify x sub beta, capital X sub beta, with this kind of looks like a code. X sub beta tensor 1 plus 1 tensor X sub beta. And these are going to be elements in our universal enveloping algebra of big factor G. But then what we do, I mentioned, we're going to extend the scalar. So what do we mean? Well, U of G, because big factor G in a sense contains big factor H, then we have U of G as a module of U of H, and R is also a module of U of H as this localization. So now we can tensor them together, these two modules, and now we have R kind of thought of as the scalars instead of the complex numbers. The reason this is because the algebra we generate, if we only look over the complex numbers, is not necessarily finite dimensional, probably really much not so. And this gives us an idea of kind of how a finitely generated algebra is. So more notation is x sub beta tilde. The motivation here again is to kind of think about how we saw tildes and stuff before. This was this is the background for a different case. But we had this complement. And the idea is, okay, instead of plus, you just put minus. Like, that's one way you can think of it. Together, all the elements, the capital X the betas, little x tilde betas, when you take this span and take this sum, you get this two copies OSP12. So in one case, you just think of like, I'm going to add like x sub beta tensor 1 plus 1 tensor x sub beta. In the other case, subtract. And like both of those will give you an OSP12 that you put together. So we have capital H here in this case. Again, it's kind of this diagonal embedding of the little h from OSP12, MID, and then H tilde. So these are all the elements that kind of like, we start off with OSP12 elements. We have 5 basis elements. And then all of a sudden we get not only 5 in terms of the capital X of betas. So we have like a capital X of alpha and all these things. We're also going to get tilde. And we're also going to get the H and H tilde. So it's like we double our elements. All right. So now that we have like all these elements, what are we going to do? This is where we create the diagonal reduction for OSP2. The main points here is we're going to have some kind of ideal and we're going to quotient out, or it's going to be kind of the factor that's quotient out from its normalized there, which we will see in a second. The reason this is called the diagonal reduction algebra OSP12 because a lot of these things are built on certain maps or embeddings. Before, it was SO2 going into this algebra differential operators, the Val algebra. Now, excuse me, just to make sure I said SO2 into the Val algebra. Now we're taking OSP12, the least superalgebra OSP12, inside of 2 copies of it. So how does this work? I mean, this is against the notation. We have this first part of the sum. This is the left ideal U generated by the upper nilpotent part of our lead. Well, it once was part of the Lie superalgebra, but now through all these maps, like we got bigger and bigger algebras, you can think of it as like the left nilpotent part of U. In other words, when we first saw OSP12 break down into 3 parts, we can do something similar for U itself. And it will look just like we had where we had like an n plus and n minus like a center part. So we have this left ideal generated by n plus, and we have a right ideal generated by n minus. And together this sum is a vector space or super space. And what the reduction algebra, one way to view it is we're going to basically look at the coset space, the double coset space. So U quotient as a vector space, not as an algebra. But it turns out that you can place a certain product, this is the diamond product, on that double coset space. So this is one way that the diagonal reduction algebra shows up, or how reduction algebra generally can show up. It's like you take something, like, okay, this is just a vector space or just a vector superspace, but this diamond product shows up, and it's because of something called the stream of projector. The stream of projectors were studied over 30 years ago, 40 years ago, Tolstoy, and you can read more in paper have with Jonas, the diagonal reduction algebra paper. We've seen the references on kind of how this is developed, but it gives us an associative product on the double coset space. So these the kind of the big picture here and why we did all that work, why we did localization, everything, is because instead of having an infinitely generated algebra, we have finite many generators. So those 5 elements that we started out with OSP 1.2 have now kind of found their image in every bigger algebra we looked at, and now we use bars. So if you want x sub beta bar is the image of or a representative, excuse me, you can think of them as yeah, like the image in each kind of quotient we build up. So whether we are embedding and then localizing and then quotienting, okay, where does x alpha go to? It goes all the way to x alpha bar. And similarly, like H goes from H in OSP 1.2 until we have like capital H into 2 copies. Then we put it into this localized version and then we're quotienting it out. So at the end of the day, we get this H bar. So the maps is where these kind of all the decoration and adornment come from. But the heart of it is that we started with this 5-dimensional least algebra, and through the certain mappings, we get these elements in this bigger algebra, and this is precisely the algebra that's going to act on primitive vectors. So the claim, what we showed, is that, or kind of more explicitly, is like say we look at polynomials in one variable, tensor C12. So I said, okay, what is this whole notation? You can think of this as the 3-dimensional complex vector space. But now we're going to consider some parity. So the 3 basis elements like V0, V1, V2, I can write this out another way for us. So in the question part, just to give a picture, you can think of this as like a column where there's parity based off the position of the one. So this would be an even element. In this vector space C1, 2. Oh. Now we have the other 2 elements, V1 and V2 in terms of the basis. And now we have a 0 in the top position. Hence, this is why we have the 1 here. There's only one place where you're going to have a purely even element. And then 1 here, 0. And then lastly, 0, 0, 1. So this is what we mean by parity, in this case for C12. And this is what we call the natural representation of OSP12. I've said this a lot, OSP12, but OSP12 can be defined as linear transformations of C12, like kind of by definition. So the X on C12, that can be realized as 3x3 matrices, and in this case, the 3x3 matrices would act on these columns, these 3 rows. So when we have, oopsie days, goodness gracious. So when we have OSP12 acting on polynomials, well, that's from kind of a similar realization as before. There's a way of OSP12 to map to the Val algebra, kind of like SL2 was. And so it will act as differential operators on the polynomials. And then we put those 2 modules together through the tensor product, and we can ask, okay, what are the primitive vectors? Now that we built up a bigger module, how will we actually decompose it? And that was the work of my thesis. And but we also had bigger questions. Well, we don't necessarily need to have C12 over here. You can have other finite dimensional vector spaces for OSP12. Tensor them, create this module, and then try to figure out what are these kind of building blocks, decompose it into simple modules. So this is an example where if you build up these polynomials tensor C12, then elements will look like some polynomial tensor like this. like V1, V2 and such, like we have sums. It turns out these three elements are primitive vectors. I think there's a slight, yeah, so this should be shut off here. So we have three elements, and that's the way that this module decomposes, meaning you take one of your primitive vectors, you act by those three, one, two, actually more precisely you with developing algebra, and that gives you a submodule. So not only did we do this together, Jonas and I, in the paper, looking at the algebra, kind of verifying things, and then going forward, and we did a little bit about the algebra in the first paper. Well, we did a lot about it in a sense. We had the generators and relations of the algebra Z, but then we went ahead and studied the representation. So I should say the algebra Z is studied in the first paper. The representations are studied more so in the second paper. That would be more accurate. But again, the big thing to take away is not necessarily that we have papers and stuff, was the very beginning idea. So if you allow me to scroll back and say, what did we do? We had this question, say like if we have a Laplace's equation, we have a certain Lie algebra, can we actually move from solution to solution for a particular equation using algebraic methods? So now this opens up different ideas like, okay, you can throw out all kind of equations. So Jonas and I started working on Maxwell equations. You have, again, more equations of these system equations that are born from trying to figure out primitive vectors. And you can just kind of keep your mind open, especially, we have linear operators involved, differential operators. Can we say more about not only the solution space, but the algebras themselves, the active solution space, and what are these, and why does this work so well? There's been some theory that written about it, but I think there's still a lot of space to do this, especially in the super world. In fact, that diagonal reduction algebra that we kind of went through quickly, that's the first, at least recorded case of writing about the diagonal reduction algebra associated to elite superalgebra. That's not also the algebra. So again, that's the goal. That's the why for me, and I hope that talk was informative at least. That's it. Thank you all.
Thank you, Dwight, for a really nice talk. I really like this example of Laplace's equation. Just as something that I can latch onto because it's easy to see that the solutions you get are actually solutions of Laplace's equation. I have some like little notebook calculations here.
Okay,
Can I
great.
ask a question just about so going back to like maybe the next slide where you introduce the three, the F, H, and G for this particular example?
Did I go here, right
Yeah,
here?
yeah, right there. Yeah,
Mhm.
right there. Okay, so what you're saying is that like the solution space for Laplace's equations, at least Laplace's equation, at least restricted to the polynomials, can be written as CF direct product with CH direct product with CE. Um, is that what I'm understanding?
So I hope I didn't write that. Just want to make sure because the first thing is that SO2 itself, that Lie algebra, can be realized um as CFCHCE, where these are the FHEs. So that's
Okay.
the first part. In other words, these are, I think of these things very abstractly, but there's concrete examples in a sense. If you were to write down the multiplication table, like what does it mean? Well, I should have been more precise to say that the multiplication here is the commutator. So if you do H times F minus F times H, the result should be -2F.
Okay. Okay. Yeah.
So that's what I meant by the CFCHCA here, but it involved the Laplacian. Like in other words, like the Laplacian is sitting as an element of SO2. In particular, the scalar multiple of it is we're seen as a basis element of SO2, but you can scale the basis.
Okay. Yeah, yeah, okay. I think I see what you mean. And then the primitive vectors you had defined as the kernel of E, which is exactly what we're looking for here, the solutions of Laplace's equations. Nice. Yeah.
Exactly. Yeah. Thank you
Thank you.
for
Thank you
helping me
very much.
through.
Yeah.
Thank you.
Does anyone else have any questions?
I do feel if no one has questions, I feel like I should have answered another question more particularly about like what OSP 1.2 is.